think that we can start, maybe? Okay, so welcome to this second day. Just a question that I forgot to ask you yesterday. How many of you program using Fortran? 3, 4, okay. How many of you program using C? Okay. How many of you don't use C, neither Fortran? Yeah. It was a double check because, no, I don't program at all. Okay. Okay. Wonderful. No, that's because typically all the things that we show here are thought to be in Fortran or C, because typically those are two low-level languages that are widely used in HPC. Okay. Probably now C++ is also emerging more in the HPC, but in general, everything that it's for C also more or less is valid also for C++. Well, more or less. Today we will see OpenMP. So we will see this approach to the shared memory parallelism. And the idea is that today I will recap something that I already told you yesterday, very, very shortly. And we will check how to make a program parallel using OpenMP. And I've put some exercises during the lecture. Some of them are quite easy, so we will do this kind of exercises in the morning and in the afternoon. A couple of them are a little bit more complicated, and maybe they will require some more time. So I will try to explain you the exercise, and then I will recommend that you can do that in a later moment. Compiti a casa in Italian. Okay. The recap. Parallel paradigms in a nutshell. Distributed memory. Each process has its own private memory. Exchange buffers, data buffers, using messages. This is implemented, for example, using MPI, so the message passing interface. Shared memory. Processes can access the same memory address space, and this is implemented in OpenMP and in pthreads with a lot of differences. Here we will focus only on OpenMP because it's the de facto standard when parallelizing scientific applications. You know already what are the limitations of MPI. I already discussed that yesterday. So what is OpenMP? OpenMP is a standard. So the standard is a collection of instructions and rules that are elaborated by the OpenMP Architecture Review Board a year by. So this standard consists of compiler directives, but also runtime routines and environment variables. So we have these different things that are altogether the OpenMP standard. Compiler directives that are meant to be put in your source code in order to say to the compiler how to make it parallel. And then there are some runtime routines and environment variables that can set up the parallel environment. So to say, for example, how many threads do you want to exploit, in which way do you want to parallelize your workload, and whatever. The idea is that you have some workers or threads. There are a lot of names, but you should understand that this is the word by which I mean the parallel entities that work together, that in parallel cooperate through the access to the shared memory. Okay. You will see that differently to the MPI, this is a quite local model of parallelization of the serial code. That means that you can start with the serial code, you identify what are the bottlenecks or the hotspots, the hotspots, not the bottlenecks, the hotspots in your code, and you decide to make them parallel. This is quite different from MPI, because in MPI you should start thinking about the partitioning, so how you share your work, and then you set up the messages that you need to perform the work. In this case, this is quite different. So in this sense, the approach with OpenMP permits to perform an incremental parallelization. So you can see an hotspot and you decide to make it parallel. It's okay. So I decided to increase the parallelism of my code. I found another portion of the code that can make it that I can make it parallel, and I can do it. So it's an incremental work. The history is now quite old history. The first standard was established with Fortran in 1997. Then we had a continuous evolution with some steps, and in 2005 there was the version supporting C++. Then we had some years without not much work, but now we are evolving towards OpenMP 4.0 and OpenMP 5. There is something that is important to say, that up to now I'm talking about the standard. So as I told you, the standard is something quite abstract, because it is a set of rules and directives. And on the other side, when you want to use this standard, you should rely on the implementations. So you have a set of rules, and then from the moment in which the standard is released, the compiler vendors or the GNU or whatever should implement the rules into their compilers. So there is typically a lag between the release of the standard and the implementation of the features of the standard into the compilers. If you look in Google, you can find some plots in which you will see what are the features of the standard and what is the release of the compiler, and you will see some check where the features have been implemented. Okay. Uniform memory access, not uniform memory access. Already you know that. The difference is that in the uniform memory access, all the cores or the CPUs are the same time to access the memory. In the not uniform memory access, or NUMA, there are different access time to the memory, in very short. Okay, but let's go to the detail of what are the threads. In general, a process is an instance of a computer program, and there are some things that characterize a process. In particular, process is characterized by the machine code, that is the translation made by the compiler from the source code to the machine code, so some text. Then you have global variables, so data, that are also called data heap. Then you have the stack, in which you have the local variables. And then you have essentially a program counter, that is a pointer to the instruction to be executed. So the heap, the text that is your source code translated to the assembler or whatever. Then you have the stack and this counter that points where you're progressing your execution. In the
thread is a process at the end?
No, that's a process.
And so what's the thread?
Wait, here I'm talking about threads now. Okay, if I'm performing multi-threading when I suppose that my process can contain several concurrent execution flows. Okay, in this schema here, okay, everything is serial. I don't have threads. If I permit to have several concurrent execution flow, I permit that I create some threads. Each of them has its own program counter. Okay. Before I had only one execution flow. Now I have more than one. Each thread can have a private stack, so I can have a part of the memory that is privately accessible for this thread. So part of the stack is made private to the thread. And then the execution can be executed permitting to each thread to access the global memory. Okay? So in general, the thread is a way to execute in an independent manner the program flow, okay, in which I can define a private part of the memory and a public part of the memory. Let's go to the execution model of OpenMP. OpenMP is based on a fork-join model. That means that when I start my program, the program is configured as something in which I have only one flow of execution. In other words, I have only one thread, and I will call it the master thread. Then I can make a parallel region in which I fork the execution. I can create several threads. Each thread can perform the execution of the code in parallel, of the code that is in this region that I just started. Then I can decide to stop the parallel region, and I will just join all the threads to recover the main thread or master thread. This can happen many times. All the times that you want to create a parallel region inside your code, you will fork the execution, creating many parallel threads. Okay? Okay. The memory model of OpenMP is consisting on the fact that you have, as I showed you in the previous slide, you have all the shared memory to which all the threads can access. And then each thread has its own private memory. Okay? When this is also something that is consistent with the fork join model, because when I didn't fork the threads, what happens is that I have my memory and I have only the master thread. When I create a parallel region, what happens is that I have all the threads, each one with its private memory. Okay? The directives are, so I told you that this is based on directives that are inserted into the code. The thing is that there are those directives that have a given syntax. For C, you have a hash, and then there is pragma OMP, and then the directive. For Fortran, you have this sentinel here, and then OMP, and the directive. This is quite useful because those messages are interpreted by the precompiler. Okay, so if you don't want to use OpenMP, just skip to put the flag, and those messages will be interpreted as comments. If you want to use OpenMP, you add the flag to the compiler in general, and during the precompilation, those will produce a code that is OpenMP parallelized. Okay? In general, there are also, this is the basics, but in general, there are also ways to make everything more complicated or sophisticated. And then you can add clauses or specifications that are meant to add information to the directives. For example, you will see later that you should manage what are the variables that you want to make private or public. You want to define, for example, some information on the control of the execution. For example, how many threads do you want to use? What is the work distribution? What is the scheduling? So in general, this is the starting point to which you can add a lot of specification. Okay, I told you that there are several ingredients. One is the precompiler directives. The second one are environment variables. So there are a set of environment variables, a lot of them, that can specify something related to the execution. For example, the first one that is by far the most used is to set how many threads do you want to use. Okay. In general, what happens is that you have your code. You put sometimes directives that say, okay, now you can create the parallel region. But in general, how many threads is specified by an environment variable. For instance, this here. If I set this OMP num threads, for example, equal to 4, then each time in the code there will be an instruction to create a parallel region, it will create 4 threads. Okay? There are other instructions that maybe will be clear in the next futures. This is, for example, to define what is the stack size. So how large is the memory for the private variables. There are something that is interesting because you see that sometimes it's interesting to understand how the threads are bound to the physical resources. Because up to now, we are in an abstract level with respect to the physical resources. I'm just saying I want to create, for example, 4 threads. Then how those 4 threads are bound to the physical resources, so to the cores, is still not clear. Okay. Well, there are a sort of instructions that can explicitly say, okay, I want to put 1 thread here, another thread there, and so on. Okay, all these other things are more advanced, but so there is no sense to discuss them right now. Okay, more or less the same thing that you can set putting environment variables, okay, can be specified using runtime functions. Okay, so you can decide, for example, the number of threads at the execution just putting this function here inside your source code. Okay, so if you decide that the number of threads must be fixed for your application. So instead to decide the number of threads using an environment variable, you should decide it putting this call to this function inside your code. Okay? This is not a good practice, because every time you bury something inside the code, then it's very difficult to be controlled. So a good practice is to decide these things outside the code, putting some environment variables. But in general, the thing is that almost everything that you can set using an environment variables, you can also do that using a call to a runtime function. There are things that instead are helper functions that are not that have no equivalent using environment variables. For example, there are functions that can set the elapsed time. So if I want to temporize my code putting some clock inside, it can be tricky when you are using parallel regions. So one of the tricks is to use those helper functions provided by the OpenMP standard. There is another thing that is quite useful. Yeah, there is something that is wrong on this slide, because OpenMP is not a library. But in general, this is because OpenMP is providing also runtime functions. So if you want to if you work only with directives, okay, and then if you don't want to use them, it's very simple, because just omit to put the flag at compilation time. Okay, so you have your directives into the code. Okay, then you don't want to use them. Just don't put the -q OpenMP or -f OpenMP, and those directives will be interpreted as comments. But if you put some functions, for example, something like that, okay, those are called to regular functions. Okay, so if you don't put the flag something OpenMP, then it will try to use those functions. Okay, so the thing is that I should try to put something like conditional compilation to skip the call to these functions. For this, there is a macro that has been defined when you use the flag for OpenMP. So every time you add the flag OpenMP, there is this macro defined that is _OpenMP. Okay? So a good practice is every time you want to use this function here, you should wrap them inside this if-def with this macro _OpenMP. Okay?
Each call to one of those functions, I have to put it inside.
Yes, because in this case, if you don't want to use OpenMP, so if you don't put the flag to use OpenMP with the compiler, this is not defined. So the function will be not called, and you will be continuing without problems. Okay?
I will put it before the else, right? The function.
Yeah, here you should put everything that you want to call with OpenMP. There, if you don't want to, don't use OpenMP. Not use. Okay. Okay. What are the flags? They are quite different for different compilers. So sometimes they are also changing. For example, this is for GNU. For IBM compilers, it's a mess, obviously. For I don't know if the Sun compiler still exists. For PGI, probably it's different right now, and for Intel is of course, different. It's dash Q OpenMP. So this slide is a legacy slide in which I forgot to update the flags. But in general, each compiler has its own flag. If you are familiar with one compiler in particular, then you learn how to use this option. Okay, before going on, there are any questions about that? Yes, please.
Can you please comment a bit about the standard C++ thread?
Okay. The question is about commenting the C++ implementation of threads. The answer is that I'm not so skilled about C++ to be able to comment about it. Yeah, I know that this is, so I know about the existence of this other feature, and I know that this is more or less adopted, but the problem is that everyone that you want to interface with something that is not C++, then it's difficult, because OpenMP is a standard implemented almost by any kind of scientific library. If you want to do something with C++ thread, then you should use only C++ components or libraries. So this is the only backside of thing. But it's as I told you yesterday, C++ was not the most popular approach in scientific high-performance computing. Now things are changing very much and quite fast. So probably if I come here next year, the story will be different. Okay, other questions? Yes?
Is the stack physically located in the cache memory of the chip of the CPU?
No. The stack is an abstract concept, and it's not resident in the cache. The mechanism of cache are completely something that are not dependent on what are the global and what are the local memory. Okay?
So they can be in the RAM memory of the
Yeah. In general, yes.
kind of slow memory.
Yeah, so the caching mechanism has nothing to do with the level of the memory in terms of cache or heap.
So, using the flags you showed before, we automatically define the OpenMP underscore OpenMP variable.
Yeah. Yes. Okay. Great. The coffee break is 10. Okay, perfect. Okay, let's start with some practical things. So we understood that we start our execution in serial, and then we can decide that as the given point, I want to create a parallel region. There is the parallel construct. It's the construct that is made like that. Just, okay, you know, this is the prefix that you should use for the OpenMP directives. Parallel simply starts a parallel region. So here, with the parentheses, I will put the code that I want to execute in parallel. Okay? There are some syntax differences between C and Fortran. Okay, so for the C, I should use the brackets. For Fortran, I should put an end parallel statement when I want to close my parallel region. Okay. Hello world, very simple. So I have this function, and here I create an hello world call. Depending on how many threads I'm using, okay, it will print several times hello world. Okay. look here, there is no specification of the number of threads. Okay? So I should specify it from outside. Okay?
Sorry.
Yes.
Sorry if I'm not asking, but for C++, is something similar to that?
Yes.
Using C++ as architecture?
Yeah. Doesn't, if you use plain C++, it's exactly the same.
Excuse me. You should specify the number of threads, or you can specify. I mean, if you don't specify anything, it will use everything available. Yes,
the typical default, if you don't specify what is the number of threads, then it uses all the available threads. But in general, this is not always true. It depends on the system on which you're running. Because a system administrator could put a hidden environment variable, and you don't know anything about that. So it's always better to check. Okay. So you understand that the main problem is to understand if a given variable is shared, or public, or private to the thread. Okay? It makes a lot of difference. So it's very important to define what is the scope of a variable in a parallel region. For shared variables, of course, there is only one instance of the data. You remember the cloud, that is the shared, the shared memory, and then you have all the private ones. In the shared scope, there is only one instance of the data that is accessible by all the threads. Okay? It's important to remember that threads can read and write the data simultaneously. Okay? Simultaneously under the logic point of view. Of course, then the data will be serialized in some way, but you don't know which is the order. Okay? Because all the threads can access the same address space. Okay? Then there is also the private scope. So each thread has a copy of the data. Okay? So when I define that a variable is private to the in a parallel region, what happens is that when I fork, each thread creates a copy of this variable. Okay? The other threads cannot access this private copy, and the changes are visible only to the thread that owns the data. Okay? This is very important. Since this is a copy, in general, unless you specify that in a different way, the values of those private data are not defined when you start the parallel region and when you close the parallel region. Okay, so you just create a copy, but you do not create the content of the buffer. Okay?
It's random.
It's not defined, so it's something that you don't know what could be.
The variable is defined, but the content,
Yes.
its value is unknown.
Yes, exactly. Okay, the variables, unless you specify differently, are shared by default. Okay? You know that defaults are very, very dangerous. So in general, there is a clause that permits to say what is the default. Okay? The default of the default is shared. So if you don't specify anything, all the variables that you have inside the parallel region will be shared. If you want to nullify the default, you should write default none. Okay? On the other hand, but this is dangerous as well, you should decide that the default is private, and that you should put default private. But this is useful only on small cases. I know that maybe you are lazy, but the good practice is to specify explicitly what is the scope of each variable that you have inside the parallel region. Because when you debug, you can see, okay, this is shared, this is shared, this is shared, this is private. And say double check that it's very, very important to perform. Okay, so now it's time for the first exercise. Unfortunately, the source code are not available as a text. So the only way to do the exercise is to go on this page, and then from there you have the text of the exercise, and then copy it and paste it somewhere where you have a compiler. In general, okay, you can use the accounts that I provided yesterday, but if you have some places in which you have a compiler, you can also run there. The only thing is that you should try to execute this code, putting and removing the flag for OpenMP. You see that this has nothing too particular. Yeah, since there are some functions, for example, no, there is nothing that is particular. But in general, there is some libraries that should be included only when you use OpenMP. So, okay, this is the function that I need to link with OpenMP. Okay. Okay, so the idea is try to copy and paste locally this source code, and try to compile it and run it. And there is a small error here. So what do you? Okay, try to see if it runs, and then I will tell you what is the error. Maybe you will notice by yourself or not. Okay, I think that now we have some time until the coffee break, and then after the coffee break we will review this exercise. This morning is terrible. Whoa. Okay. Okay. I think that probably you already looked at the solution because it was on the next, very next page. But okay, just to comment a little bit also based on what I saw on your experiences. The first thing is that most of you used all the available threads. So just in a couple of cases, I see somebody exporting OMP num threads equal to something. But in general, that's okay. But what happened is that if you didn't set the value of the OMP num threads value, variable, this one, the thing is that you are running with all the available threads, maybe 12 or I don't know, something like that. Okay, that's fine. The first thing that could happen if you run this code is that you get a hello from, and then in some cases the same number, for example, hello from 3, 3, 3, 4, 1, 0, while what you could expect, what you may want, is to have hello from 1, and hello from 2, and hello from 3. So each thread is expected to print his hello word. Okay, why that happens? You may already know that the problem is that here, in this region, the variable IM is a shared variable because it is defined here, and here I didn't put anything to specify the scope of this variable, so by default this is shared. What happens is that each thread with an order that we don't know put the value of his number to IM, and then it prints this hello. So you don't know which is the order of the threads accessing to the assignment of this variable. So the result is completely not deterministic. There are two options to fix this problem. One is to, okay, there are two things that I saw. Just one is, let's say, correct. I saw that some of you shift this definition of the variable inside the parallel region. If you define something inside the parallel region, that variable, by definition, is private for the thread. Okay? So in this case, it works because each thread has its own private variable. So he assigns the OMP getThread number to that private variable, and it prints the name of that variable. On the other side, this is not very much correct because in principle, I would like to preserve the shared scope of this variable. So I just decided to change for all the code the scope of the IM variable. The correct way, the most correct way, was to define here that this variable was supposed to be private, writing after parallel, private, and IM between parentheses, okay? That was the thing, and you can find it on the next page there, that I cannot load right now, but anyway. Okay, so what you just experienced is the data race phenomenon, where when two or more threads can access at the same time a shared memory location asynchronously, so in different moments, but without any locks. So in this case, you have accesses, and you don't know which one is writing or reading the variable and in which order. Well, Okay, so in this case, the resulting values, the result is not defined. If you remember yesterday, at a certain point, I said that sometimes the results can be not deterministic. This is one of the cases, okay? The fix for this problem was quite simple, and in particular, if I was a wise programmer, I should have took care of defining each variable defined inside the parallel region. I just let the default, and I was punished by this data arrays. Okay, there is another thing here. This is this critical construct. This is, in this case, it was not really needed, but let's check what is a critical construct. In some cases, one of the possible solutions for data arrays is to use the critical construct. When you use a critical construct, you define a block inside the parallel region that can be executed by one thread at a time. In this way, you avoid simultaneous access to shared data. But, okay, there is another thing that you can also associate a label to each critical region. The problem, in this case, is that if you use too much the critical construct, the thing is that probably you can be more sure of your results or the behavior of your code. On the other side, you are making your parallel code a serial code. Because when you have a critical region, you cannot permit parallel operations. In some cases, this is necessary. For example, when you want to update some variables, and you want to be sure that the variables is updated just once by each thread, you should use the critical construct. The idea is that, okay, but in general, the parallel is more efficient when you have a very large parallel region and when you have just a few small critical regions. This is one of the cases in which, for example, now I don't want to see what is the thing here. Here I have a parallel region. Here I should update some sum, and I put a critical region. In this case, since the critical region is just made by one single statement, I don't need to put the brackets. And this is the only case in which the brackets are not necessary, if I'm not wrong, or they are. No, okay, no. I put here an extra bracket, or I missed one there, but okay. In general, the thing is, here I have this parallel region, and here I have my critical part. This is quite important to know. There is another statement that is very, very similar to the critical, and that is the atomic construct. I didn't put a slide for that, but when you want to have a critical region that just affects one single statement, as for example in this case here, instead of the critical, you could use the atomic. Okay, so if you use the pragma OMP atomic, it will create a critical region for the following statement, for the following instruction. Okay. Now, until this moment, what we just discussed is how to create a parallel region and how to create a kind of lock, okay, creating a critical region. Let's see how we can share the work, because the parallelization is also about having some kind of workload, and making it shared among the threads. In general, what happens is that in order to make a parallelization, what I need is the parallel construct, the critical construct, and maybe I would like to get what is the identifier of the thread and the total number of the threads. That's enough, because I could assign, if I know what are the thread ID, I can assign some work to a given thread ID. Okay, just moving the indexes in a wise manner. Okay, but there is something that is this is something that sometimes can be a little bit inefficient, and sometimes it's also a little bit tricky. You see that in this case here, what I did is exactly this thing here. I got the thread ID, I got the number of threads. Here I had a loop, and I just split this loop, giving to each thread a part of the loop. Okay, this is possible like that. Yeah.
Inefficient in this case means necessarily slow also.
Yeah. Yes. Yeah. Means that it can be, for example, in some cases, it can result in a wrong work sharing on the case of load balancing. In some cases, you could have some part of the loops that are not balanced with the other ones. Okay. See.
In the previous slide, where is PSUM defined? Is a private variable?
PSUM is not a private variable here, so it should be. This is a snippet from a larger code, so probably this is outside, so it's supposed to be shared.
But if it's shared, it's not a race condition, like many threads updating PSUM?
In this part, there is not a race condition, because each thread contributes only to a part of the sum. You see that the index in which the cycle is running is given by the thread ID. Okay, so each thread ID just performs a part of this for loop. Okay. In this case, there is no race condition, because there is the critical. Okay.
PSUM is private.
Hmm?
PSUM is private.
PSUM is private. Yeah. No, in this case, it's not private.
So
Looking only at this snippet of code is not private.
Yes, but if you
So you have a race condition.
private.
there is a
What if both are writing on PSUM?
PSUM,
You may miss an increment.
Here. Okay. But here, you have the contribution only coming from one part of the loop. Let's suppose that you have two threads and a loop with two items. The first is given by the first loop, by the first thread. So first iteration of first thread. It accumulates here. The other does nothing. For the second iteration is made by the second thread, and just the second thread contributes here.
Yeah, but that's a sum plus
Yeah, okay. This is equal to PSUM plus x of I.
my position is that there is
there are different threads writing on the same global variable, which is PSUM.
But you just
no, you're also
it's not
using
a
the
condition
value.
because it's the sum operation is atomic.
No.
It's not set because you have two cores that are running a
Okay.
sum operation. You have to add.
For the moment, let's move the discussion for later moment. Yeah, I'm not convinced that this is a race condition, but I can change my mind, of course. But okay, the thing is that let's try to move to the next step. Maybe there is a race condition.
Condition. Yes.
Because you need the value of this sum.
Do you have a full load?
You ruined my morning. So
You need a full code.
yeah, but no, I need some paper and something to check. Okay. Okay. I can fail sometimes, so this is for sure. Okay, work sharing. So in this case, in which maybe I can have a race condition or maybe not, there is a way in which I partitioned my work on the different threads, and I used here a critical region, and I used there a parallel region. But there is some other methods to perform work sharing. There are some work sharing constructs. The idea is that I would like to make this kind of work sharing more simple for the programmer. So there are some work sharing constructs that distribute the execution of a given parallel region to the different threads. Typically, the character of those work sharing regions is that they have an implicit barrier at the end of the work sharing region, and this barrier can also be removed adding a no-wait clause. What are the work sharing constructs? One is for the for do loops, one is for the sections, one is for the single, and another one is called the work share construct. Now we will focus much more on the first one, but for your knowledge, there are also some others. The loop construct is the most useful because in a very large number of cases, the hotspots of the applications are based on loops. So the most intuitive and straightforward approach is try to make the loops parallel. So the idea is to take a loop and try to distribute over the threads the iterations that are contained in those loops. By default, the iteration variable is private, and if you have multiple nested loops, the inner loops are executed sequentially by each thread. Okay. There are some rules about the scope of the variables. In particular, when you have outer and inner loops. In Fortran, the inner loop variables are private by default. In C++, they are not. But in my opinion, the best is to put explicitly the scope of each variable. There is a strong requirement for the parallelization of the loops, is that you don't want dependencies between the loop indexes. In some cases, that can be removed if you have some dependencies. In some cases, not. But in the latter, you should avoid to parallelize those loops. OK. It's quite simple. In C, you should just add the for keyword. And here, this is the loop, and then the bracket. This loop here will be parallelized over the index I. In Fortran is more or less the same, in which you should have two statements, one at the beginning and one at the end. It's important to remember that all those all the loop construct should be inside the parallel region. Okay, So I assume that before this pragma, there is another pragma OMP parallel. Okay? So you cannot put this construct outside the parallel region because it doesn't not work. This is an example. Okay. This is the parallel region. This is the pragma OMP4 region. In this case, I didn't specify the scope of the variables because I have the I is private by default, but each thread is writing just a portion of the A array. Okay? So A is shared, but each thread is touching just a part of this array. So in this case, there is no race condition. Here there is another pragma OMP4, and here the parallel region is closed. Okay?
So we don't need to declare I again inside the parallel.
No, A is a shared variable. B is a shared variable. C is a shared variable.
The counter I.
I is private by default because it's the iteration index.
Is declared.
Okay. Well, there are cases in which I may have two nested loops in which I don't have dependencies between the two different indexes. And what I can do is to collapse in a single cycle for loop the two different loops. This is, in general, this is something that the compiler already does. But what I can do in this case is to try to, if I just put pragma OMP4, what OpenMP does is just to parallelize the outer loop. Okay. In this case, saying collapse 2, what happens is that the compiler makes a loop fusion. So here I will have a single loop running up to all these index years, and it will parallelize those two loops.
So a single loop will with n times n elements.
Mm-hmm.
In this case.
Yeah, and n plus m. Yeah, yes.
So what happens if there is a dependency? Like I get some error or unexpected behavior?
I think you should get an error. Not so sure because yeah, you should get a compile time error. Yeah, at least it's something very, very tricky and hidden, which the compiler is not able to resolve the dependency, but it's quite difficult. Okay. Okay. Now the question before was why it's better to use the work sharing construct rather than do it by yourself. The thing is that the work sharing construct also takes care of the load balancing. So it tries to distribute the work in the way that each thread has balanced the work with the other threads. There are some scheduling clauses that are meant to specify how the iterations are divided among the loops. So the thing is that in general, what you could think is that, okay, I have, I don't know, 4 threads and 400 iteration. Okay, first 100 are for the first thread, for the second 100 is for the second thread, and so on. In some cases, that could be not the best solution, because in principle, you don't know if all iterations have all the same computational weight. So there are some way to assign the workload. There are 4 different scheduling options: static, dynamic, guided, and auto. And there is the definition of the chunk size. When I just told you I have 400 iteration, and I take 4 chunks of 100 iteration. The chunk size is the amount of work that I distribute to the threads. So let's see what is the differences. The static scheduling is the most intuitive one. So if it's the example that I just described. So if I don't put any chunk size explicitly, then the number of iterations is divided more or less equally on the number of threads, and each chunk is assigned to the threads in the order. So the first one to the first thread, the second one to the second, and so on.
Excuse me.
Yeah.
But this kind of decision is made at the completion time or during the running of your code?
It's done when you. This is a clause that you will add when you put an OpenMP4. So it's here you can add schedule this kind of scheduling. Okay. In some cases it can be also runtime. Okay. So for the moment you should define it as a specification of the work sharing construct. So it's a compile time which you decide. But there is the last option that is the runtime option.
I meant the implication of this clause is a runtime effect or just a compiling time effect?
No, the effect is at runtime because when you are assigned the workload is at runtime. Okay, but the decision on the scheduling is made at compile time. Okay.
So it's static, basically.
Yeah. Okay. So think that you have the different approaches. So I say that I want that you share the work in the most simple way. So the first chunk that is 1 on the divided by the number of threads on the first one, the second on the second. This is decided a priori. Okay. Then at the runtime you will execute your decision. There is also another option that is slightly more complicated, but I can decide to have a chunk size. For example, I decide that I have 400 iterations, and I decide that I have a chunk of 50 iterations. Okay, so we start to distribute them in a round-robin way. So the first chunk to the first one, the second chunk to the second one, third to the third, the fourth to the fourth, and then I have a fifth chunk, and I will assign the fifth chunk to the first one, and so on. Okay? Okay, this is a quite simple approach. But in this case, the assumption is that all the iterations have more or less the same computational weight. Okay? There is another approach that is the dynamic scheduling. In this case, I divide my iterations in chunks of a given size. Okay? And I assign the chunk to the thread when they are ready to do some work. Okay? So I start just like in poker. I assign the chunks to the player, to the threads here. When one of them has finished the work, I can give them another chunk, okay? In a way that if the chunks have not the same computational weight, what happens is that I can provide immediately with another one, okay? In general, this is a very fine-grained approach when I don't define the chunk size. And then in this case, the scheduler just assign one iteration. Okay. In this case, it's quite difficult that this is efficient because there is the overhead of the scheduler with respect to the iteration workload. But this is the behavior. There is also a small variation of this. It's the guided scheduling. In this case, this is very similar to the dynamic, but the chunk size is decreasing. Okay? So I decide what is the starting chunk size. I assign my chunk to the threads when they are ready, and I decrease the size of the chunks. Okay? In this way, the grain of the assignment decreases, and it's easier to manage the workload. Okay.
So the decreasing function which is used for this, is it implementation dependent, or you can?
No. There is some rule. Now I don't remember if it's like an exponential, the number of iterations.
It's standard.
Yeah. You can decide at the runtime what is the kind of scheduling, setting this environment variable. Okay. So if you decide that you want to change the kind of scheduling at the runtime, you can rule that with this environment variable. Okay. Typically, this is useful when you are developing your code. You want to make some experiment, and you change this, and once you decide what is the best scheduling, you put it in the code. There is also another, the last option is auto. So you can use this option, and in this case, the decision is delegated either to the compiler or to the runtime system. Okay, so if you don't want to take any decision, just let it auto. Okay, this is quite important because sometimes the result, the time to solution can change. Okay, when in the cases in which you don't have all the iteration with the same weight, that can change a lot. So the idea is try to check what happens when you change the schedule. There are questions?
Let's say, for example, that I am in a strange situation, not so strange in fact, where I have one core of my processor which is hotter than another. And I have made a chunk divided my job in different threads, equally dividing the job, the work to do, all the workers. And for the different temperature of the cores, some are going to be clocked slower than others. And for this reason, one of the thread will end early than others. In this case, if they are statically governed by means of the
static schedule,
yes, we are going to use not efficiently all the cores implied in the computation.
Yeah.
Instead, with the auto-tuning way of the thing, it should be more running time, auto-governing the situation, or not.
Well, for example, in this case, okay, I repeated the question if there is somebody following the streaming. If you have, for some reasons, some of the cores that is running slower with respect to the others, if you think that it's going on a static scheduling, so each thread has a given number of iterations already pre-assigned, or if you wonder if the auto is able to detect this kind of behavior and heal it, in the first case, if you put the schedule, the static scheduling, there is no way to change the things, because the rule is that each of the threads has the same number of iterations. Something that could be more effective is the guided or the dynamic, because in this case, the scheduling first come, first served. So if one of the cores and one of the threads has a slower behavior with respect to the others, this will not penalize the other ones, because simply will be not served with another chunk until he has finished his work. That's the right behavior. So most of the time, the dynamic is the best one. Okay, unless you are very, very sure that your behavior is quite fair and you can assign the same number of iterations. But in general, this is not. Then it depends if you trust enough your runtime system that is maybe skilled enough to decide to change the scheduling, but that depends on the implementation. Okay. There is another kind of construct that is the section construct. So the first work sharing construct was about a single loop that was quite important, sorry, not spot, and I want to make this loop parallel. In some cases, I may want to identify different parts inside my code that I want to make it parallel. So I have, for example, a part of the code that can be executed in parallel with another one. So I can define two sections that are meant to run in parallel. So I identify two blocks of code. I define that they are sections that can be executed in parallel. Then each thread will receive sections to be executed. When a thread has finished to execute his section, he can check if there is another one to work on. If there are not other sections to execute, the thread will wait for the other to end up. Well, this is a good approach when you have a lot of sections, okay, in a way that you can distribute them on the threads, or if you have only a small number of threads. For example, if you have 2 threads, that's enough. But if you have, for example, 16 threads and you have just 2 sections, this is not very efficient. Okay, this is the syntax. So I identify those 2 sections. In this case, those 2 sections will be executed in parallel. The first one will be assigned to the first thread, the second one to the second thread, and that's it. The single construct, in this kind of approach in which I imagine that I have several sections, well, I can define a single block, okay? So the first thread that reach this single construct execute this block, and the other thread wait at the end of the construct. Okay, so I have just one, the other just wait, and this is, it's more or less on the same spirit of the critical. There is something that is only supported in Fortran. This is the work share construct. If I define a block here, in Fortran, then the work that is contained in this block is distributed in units of work to be associated with the threads. It never works, honestly. So it's more a source of problems than a solution. So, but just for your knowledge, there is something like that. Maybe in the next implementations will be more efficient, but right now. Okay. Again, the data sharing attributes. So again, the problem is always the same. So I need to define what are the shared variables, what are the private variables. The problem is that most of the time, people forget to define these attributes. So it's very, very important to add this default none, because this is, for Fortran people, it's the equivalent of putting implicit none when you start to write a Fortran code. So just avoid that you say, okay, everything is by default, but it's killing us. So add the default none, and if you forget to define the scope of a variable, the compiler will warn you. Okay, so let's go back to the different attributes. Shared, you already know what it means. Private, again. Now I'm going to add a couple of more attributes. One is first private, and the second one is last private. Because I told you that there is no definition by default of the behavior of a private variable at the beginning and at the end of a parallel region. Okay? So if I enter a parallel region, it's not copied the value of the variable, just the fact that the variable exists. If I want to copy the value of the variable from outside the parallel region inside to the parallel region, I should use the first private. So first private will tell that, okay, this is my variable, now it's private, but it has the same value of the shared variable outside the loop. The last private is the inverse. So when a loop finishes, maybe I want to copy the value of the I want to copy the value that I saved in the private variable outside to the loop. Okay. Okay. The warning is quite. If a variable is defined with the wrong attribute, it can produce meaningless results. Sometimes you understand that they are meaningless, sometimes not. And now it's the time for the second exercise.
I have a question.
Yeah.
So when we use last private, the slowest of the threads will be the one to modify the value.
Yes.
The last private.
Let's check if I can. Se ha cambiato qualcosa nel frattempo? No? Facciamo una cosa. Intanto provo a vedere se riesco a vederlo con il mio. Don't look at the solutions.
There are the solutions also?
Yeah.
It's too easy.
Sempre nemmeno il mio si autentica adesso. Ok, adesso è andato. Ok. Andiamo sopra, Ok. Exercise number 2. The following code perform a serial matrix multiplication. In particular, it's here. This is a matrix multiplication. The exercise is to try to parallelize with the OpenMP the most important loop. I just showed you what is the most important loop, so part of the exercise is already done. If you want, try also to add the timing function before and after the loop and print what is the elapsed time. Just for equality, I will show you on the Fortran code which is the most important loop. It's this one. Okay? It's not that difficult, so don't look at the solutions. So please, now I think 20 minutes. 20 minutes plus a bonus of 10, maybe. or 4 threads. And then you should see some difference.
I charged 1,000 for threads, and the parallel solution is
Slower.
times slower than the series.
Nice. On which system? On Cineca?
No, on my system.
Oh, okay.
What's on mine?
That could be because maybe, okay, there are a lot of side effects when you are using a system that is already busy doing some other thing. Because the worst effect is that the threads can migrate from one core to another. If they migrate, they lose the data locality. If they lose the data locality, it's a nightmare.
Even if I have a system where all the cores are working, occupied with threads,
setting some environment variables that can change from system to system. But there are ways to bound the thread to the cores.
how can I see that threads are migrating when I execute my program? By default, I have to assume that they will be.
The best answer is that you can check bounding the cores and see what is the difference with respect to non-bounded behavior.
If I see an improvement in the computation time, it means that.
Yeah. Okay.
I have one comment, but we can.
Okay. Okay. So yeah, just to repeat this comment that maybe it's useful, because sometimes you don't find any improvement, and there are a lot of reasons for this behavior. Okay, I would expect some improvement if you are on a system in which there is nothing else running. Because if there are already something running, some daemons or something which you are not aware of, the risk is that in order to balance the workload on the physical resources, on the cores, the threads can migrate. So one thread can change the core on which it's executed. If this happens, you are losing the data locality. Okay, because maybe you have some cache that is bound to one core, and if you are migrating on a different core, you lose the data that were on the previous cache. Okay, so that's the nightmare. One of the solutions in some cases is just to bind the thread to the core. You saw before that there are some environment variables that are meant to bind the threads to the core. I don't discuss this because this is really system dependent. So for GNU there are some variables, for Intel there are different ones. So just check the documentation of your compiler and the binding rules. But in general, when you want to reach high performance behavior, you should be aware of the migration problem with respect to the threads. Okay. This is old. The reduction, this is something that it's quite useful. There are a lot of cases in which there is some variables that is meant to accumulate value from the different threads. This is a variable that can be declared as a reduction variable. What happens when I declare a variable as a reduction variable is that implicitly it's created a private copy for each thread, and at the end of the parallel region, each of those private copies that are not visible to the programmer are put together in order to be accumulated in the reduction variables. This reduction clause is valid for the parallel for do loops and for the section constructs. Just to see an example, this is the construct. You see that there is the pragma OMP parallel 4. So here I have this loop in which I want to accumulate the value of the X array on the variable sum. What I can do is to declare that sum is the reduction variable on which I want to accumulate the sum. So plus means that the operation that I want to perform on this variable is the sum. There are many operators that can be supported for this operation, so sum, multiplication, and many others, also logical operators. So now there is the third exercise that probably will lead us to the lunch break that is 12:30. Yeah? Okay. So this is the, I don't know, aperitivo. So let's start looking at this one. No, Chromium, no. Troppa grazia. Okay. Perfect. Okay, this exercise is a classic exercise. There is a code that calculates the value of pi, and then this is to be parallelized with OpenMP. So in general, you see that this is the important loop. This loop should be parallelized, but you can see here that there is a sum. So this is an accumulation, and I should declare this variable as a reduction variable. And okay, I already said anything. So okay, there is another interesting part, but this is only for the nerds. So try to do that without using the reduction clause. Okay? And then this is for the lunch, and we will check it after. Esatto, sì. Dove non c'era un data race, ma la soluzione è stata sua. Perché PSAM era definito dentro la cosa là.
Ah, ok. Non c'era la dichiarazione.
Se non lo dichiari ed è dichiarato dentro la cosa, sì, mancava un int davanti, sì. Un int, un real o qualcosa.